Even the most advanced predictive algorithms, though built on flawless mathematics, will still inevitably collapse when deployed in real-world production environments. The failure rarely stems from the math itself. It originates from the ingestion of raw, unvalidated operational data. This is the absolute rule of computer science: garbage in, garbage out. To extract valid, actionable patterns from this chaos, database engineers rely on a 7-step framework called Knowledge Discovery in Databases, or KDD. While machine learning gets the spotlight, this timeline highlights a harsh engineering reality. Data preparation consumes up to 80% of all project time and resources. This preparation phase targets the structural and statistical flaws inherent in raw data before they reach the modeling stage. Analytics engines attempting to process raw feeds without this architectural buffer absorb the full volatility of the operational environment. The core objective of a corporate data warehouse is to provide a single, unified historical repository optimized for complex analytical queries. At the bottom tier of this architecture sits the source layer, where raw data is continuously generated by day-to-day transactional systems. These sources are inherently chaotic. They combine relational databases, external APIs, and flat log files, all generating records in completely different formats. To protect the central database repository, a staging area is deployed as a physical barrier to intercept disparate streams. Isolating this data pulls the heavy processing load off active production databases. Inside this environment, the automated ETL pipeline executes its routines. The staging area operates as an active computational quarantine zone, where records are refined before ingestion. If we step inside the staging area, we can trace the precise lifecycle of a highly fragmented operational record. The process begins with phase 1 of the ETL pipeline, extraction. The system pulls heterogeneous, unaligned data formats from various sources, dropping them into a temporary holding grid. Immediately, phase 2 initiates. This is data cleaning, the first direct intervention in the KDD pipeline. First, algorithms scan for overlapping records from different systems, identifying and deleting duplicate rows. Next, the system scans remaining records to isolate and strip out corrupted, noisy, or physically impossible values. This leaves behind empty fields. A null or missing value poses a severe mathematical danger, instantly breaking distance-based algorithms like k-means clustering. To fix this, the pipeline applies statistical imputation. As shown in this grid, the system calculates the average values of the surrounding data points in a column and uses that mean to populate the missing cell. Retaining these repaired records is critical. Discarding every row with a missing value would destroy the statistically significant sample size required for predictive modeling. By employing algorithmic scrubbing, the system preserves overall data volume while aggressively eliminating the mathematical blind spots that derail machine learning. Scrubbing out noise removes the errors, but it does not solve the problem of heterogeneous systems failing to share a common structural language. The pipeline moves to phase 3, data integration, designed to resolve structural and semantic mismatches. The system first resolves naming collisions, taking conflicting headers from different sources, like cust ID, and merging them into a single standardized column header. It then targets underlying data type conflicts, running conversion scripts to turn string characters into operable integers. Through these operations, separate and chaotic data streams are finally forced into a rigid, unified schema standard. Enforcing this strict schema alignment early prevents catastrophic table join failures when analysts query the data in the analytical tiers later on. During this step, the system also establishes uniform primary key structures across all records, maintaining strict referential integrity. Integration strips away the origin formats. It mutates isolated application data into a cohesive, enterprise-wide asset. Even perfectly clean, structurally integrated data is still not ready for advanced data mining engines. To prepare it for analysis, the pipeline executes phase 4, data transformation, specifically focusing on feature engineering. This starts with data aggregation, summarizing granular, daily transactional logs into broader weekly or monthly metrics that are easier for models to process. But a hidden threat remains: massive numerical variance. Many algorithms weigh numbers based on absolute magnitude rather than actual statistical importance. meaning a high-value column like revenue could artificially drown out a low-value column like age. The solution is a mathematical process called normalization. Here, a column containing wildly varying large numbers is mathematically scaled down simultaneously to a normalized range, fitting entirely between 0.0 and 1.0. Scaling forces all variables onto an equal mathematical footing, protecting models like deep neural networks from being skewed by large integers. With their magnitude stabilized, these transformed metrics now map perfectly to the required input nodes of machine learning architectures. Transformation serves as the final bridge, elevating basic historical record-keeping into a format designed exclusively for predictive mathematical modeling. The grueling This unchangeable stability allows data scientists to audit multi-year trends without the constant fear of data corruption. From the central repository, pristine data flows upward to power the analytical layers. The unified schema feeds the middle tier, enabling multidimensional OLAP cubes to instantly slice data. Meanwhile, normalized metrics feed the top tier, providing the mathematical foundation required by predictive algorithms. The most advanced analytics and AI models in the world are entirely dependent on the structural rigor established at the bottom tier. The staging area operates as the architectural immune system of the database. Without rigorous structural engineering to filter the noise, true knowledge discovery is mathematically impossible.